Welcome viewers. In this video we will see the electric field intensity due to a charged disk. The charged disk is available. In that we are going to see what is the electric field intensity. A disk is with a radius a meter that is uniformly charged with the charge density sigma coulomb per meter square. That is nothing but surface charge density. So a charged disk is nothing but like a CD, compact disk. The entire surface we are going to consider. So that here we are using the charge density sigma coulomb per meter square. Right? By referring this diagram, this is the charged disk with radius a meter. We have the charged disk with radius a meter available. The disk is assumed to be having several rings of increasing radius. Starting from 0, there are n number of rings are available. Starting from 0, the radius of the rings keep on increases and reaches the maximum value of radius a. In this we consider one ring at a distance x meter. The ring is assumed to be having several rings of increasing radius. In that we consider one ring for the calculation purpose at a distance x meter. Our aim is to find the electric field intensity at this point P. The distance between this point P and the center of the disk is d meters. The distance between point P and this small segment is r meter. This will be x meter. So this triangle is drawn separately here. D XR. During the calculation we can refer this triangle. So this is a small segment dx. The angle will be alpha. So when the radius increases, the angle alpha will increase. The radius increases from 0 to a. So in terms of angle it increases from 0 to alpha. During the limit we need this value alpha. Right? So we have the charged disk with radius a. It is assumed to be having several rings. We consider one ring at a distance x meter. The thickness is dx. Our aim is to find the electric field at this point P, which is at a distance d meter from the center of the ring. The distance between this point and point P is r meter. This will be x meter. So this triangle is drawn separately. Because of surface charge density, sigma equal to dq divided by ds. From that, dq equal to sigma into ds. Right. So it is given in terms of surface charge density. So the description is given here. It is required to determine the electric field intensity at point P, which is at a distance d meter from the center of the disk. Right. Our aim is to find the electric field intensity at this point P, which is at a distance d meter from the center of the disk. The disk is assumed to be formed by several rings of increasing radius. From 0 to a, they keep on increasing. Several rings are available. In that we consider one ring of radius x meter with a thickness of dx. Right. So due to this small ring, the electric field intensity will be dE due to this small charge dq. The charge is small, so the electric field also small, dE. By integrating, we will get the total electric field intensity. So another important point is the perpendicular field is 0. If we consider any object, perpendicular field, that is vertical component, will be 0. Only the differential x component is available. X component means horizontal component. You know that vertical component, horizontal component, two terms available. Horizontal component equal to total component multiplied by cos of theta. Vertical component equal to total component multiplied by sin of theta. So here vertical component is 0. Only we have horizontal component is available. Now we'll start with the electric field intensity. The general formula Q divided by 4 pi epsilon r square. Electric field intensity E equal to Q divided by 4 pi epsilon r square. We consider only small charge, so that dE equal to dQ divided by 4 pi epsilon r square. Only the horizontal component available, so that it is multiplied by cos theta. Right. So small electric field, small charge, and this will be horizontal component. So that is nothing but dE equal to this dq can be replaced by surface charge density sigma into ds. Already this is available in the near the diagram, sigma dot ds divided by 4 pi epsilon r square into cos theta. So finally we have dE equal to sigma ds divided by 4 pi epsilon r square into cos theta. Now we'll see the expression for this ds. But this S is nothing but surface area of the disk. It's like a compact disk. S equal to pi r square. You know that area of the disk will be pi r square. So here we need ds, so differentiate on both the side. So that ds equal to differentiation of pi r square. So ds equal to pi. The differentiation of r square is 2r into dr. Right? So that it is 2 pi r dr. The ds value will be 2 pi r into dr. But in the diagram we consider the x. We consider one small ring at x meter. So that 2 pi x dx. Right? ds equal to 2 pi x dx. Now we can replace this ds with 2 pi x dx. So that value is substituted here. dE equal to sigma, this ds is 2 pi x dx divided by 4 pi epsilon by epsilon r square into cos theta. This 2 pi, here the 2 pi got cancelled. So what we got, sigma x dx divided by 2 epsilon r square into cos theta. We'll take this is equation number 1. So after substituting all the value, we got this expression. Now we have one triangle is available. From this triangle we are going to find the expression for x followed by dx and r. Right, x followed by dx and r we can calculate, we can found from this triangle. So first we will find the tan theta. Tan theta is nothing but opposite side by adjacent side. So this is theta, opposite side is x, adjacent side is d. So x by d. Right. So tan theta equal to x by d, right? So that x equal to tan theta into d. You cross multiply this, so that x equal to d tan theta. Now we got the expression for x equal to d tan theta. We need dx also, so that differentiate on both the side. So dx equal to differentiation of d tan theta. So dx equal to d, differentiation of tan theta is nothing but secant square theta into d theta. So dx will be d secant square theta d theta. Right. So we got the expression for x as well as dx. Now we can go with the cos theta. Cos theta equal to adjacent side by hypotenuse. Cos theta equal to adjacent side by hypotenuse. So d divided by r. We cross multiply this. Right, you exchange these two values. So r equal to d by cos theta. So that r equal to 1 divided by cos theta is secant theta. So that r equal to d secant theta. Now we got the expression for r also. Now we are going to substitute this x value, dx value and r value, r expression in this equation number 1. Now we'll substitute this value x, dx and r in equation number 1. What is equation number 1? Sigma x dx divided by 2 epsilon r square into cos theta. That is the expression for, that is the equation 1. Now we'll substitute sigma x is nothing but d tan theta. Dx is nothing but d secant square theta into d theta. Again this cos theta is available. Divided by 2 epsilon r square. R square is d square secant square theta. Right? D value, dx value and r value is are substituted. The secant square got cancelled. Here d square is available. Here also d available 2 times. So d square also got cancelled. So what we have, sigma tan theta cos theta d theta divided by 2 epsilon. After cancelling this, we got this value. So this tan theta can be written as sin theta by cos theta. Sigma divided by 2 epsilon. Tan theta is written as sin theta by cos theta. into cos theta d theta. So this cos theta got cancelled. So what we got? dE equal to sigma divided by 2 epsilon sin theta d theta. Now we got, after substituting all the value, we got this expression. So this is due to small charge. So by integrating on both the side, we'll get the total electric field intensity, right? Now we'll go for the integration. So integral dE equal to integral sigma divided by 2 epsilon sin theta d theta. What is the limit for this integration? We need to consider entire radius of the disk. Entire radius is a meter. But the difference, that the integration with respect to theta, so that we are considering the angle alpha, right? So when the radius increases, the alpha also increases. So we are taking the limit 0 to alpha, very equivalent to 0 to a, right? So sigma divided by 2 epsilon is constant. Only we have sin theta. Integral sin theta is minus cos theta. We need to substitute the limit 0 and alpha, upper and lower limit. So sigma divided by 2 epsilon, this while substituting the upper limit minus cos alpha plus. So already one minus is there. While substituting lower limit, we have one more minus. So it becomes plus cos theta, cos 0. So sigma divided by 2 epsilon minus cos alpha plus cos 0 value will be 1. Right? So while rewriting, the electric field intensity E equal to sigma divided by 2 epsilon 1 minus cos alpha, right? So this is the final expression for electric field intensity due to a charged disk, sigma divided by 2 epsilon 1 minus cos alpha. Now we'll see the electric field intensity due to charged ring, right? We'll see that. Now followed by the disk, we will see the charged ring, electric field intensity due to the charged ring. What is this charged ring? Yes, a wire of small cross section is bent in the form of circular ring. One lengthy wire is available. Two ends are joined together and form the circular ring. So here the wire is available, so that we are using linear charge density, lambda equal to dq by dl, so that dq equal to lambda into dl. Because of wire, lengthy wire is there, so that we are using linear charge density. The wire is uniformly charged with the charge density of lambda coulomb per meter. Right, here we are using the linear charge density, so that we are using lambda. Now we'll refer the diagram. So one lengthy wire is available. Now the lengthy wire is joined together. Two ends are joined together and form the charged ring. Right, the radius is a meter. So the length of the wire is nothing but circumference of this ring. Both are equal. Lengthy wire become the ring. So circumference of the ring is equal to length. So our aim is to find the electric field intensity at this point P, which is at a distance h meter from the center of the ring. Here we consider one small segment dl. L is the length, dl means small length. The distance between this segment and point P is r meter. This angle will be alpha. Right, similarly this angle also alpha. So this triangle is drawn separately here, A, R, H, with an angle alpha. From that, if you find cos alpha means adjacent side by hypotenuse, h by r. During the calculation, we can use this cos alpha equal to h by r. So one lengthy wire is available. The two ends of the lengthy wire is joined together and form the circular ring. The radius is a. Our aim is to find the electric field intensity at this point P, which is at a distance h meter from the center of the ring. We consider one small segment dl. The distance between these two is r meter. This triangle is drawn separately with an angle alpha. Now we'll see the description. It is required to determine the electric field intensity at point P, which is at a distance h meter from the center of the ring. Right? We have the point P, which is located at a distance h meter. we consider only small charge, so that the electric field intensity also small, dE, right? So dE is nothing but electric field intensity due to the point charge dq. So now we'll consider the small length dl. At the small length dl, the charge will be dq, right? Now we'll go to the derivation. We know that electric field intensity E equal to Q divided by 4 pi epsilon R square. Due to small charge, it becomes dE equal to dQ divided by 4 pi epsilon R square. Only horizontal component available, so that cos alpha, right? So the dQ can be replaced by lambda into dl, linear charge density, right? So lambda dl divided by 4 pi epsilon R square into cos alpha. This lambda L is nothing but the circumference. I already told circumference, that is A into d theta, that is radius as well as theta. So when the circle it is rotates, the theta also varies, so it can be replaced by A d theta, this dl. So this is only the small electric field. By integrating on both the sides, we will get the total electric field. So integral dE equal to integral lambda A cos alpha d theta divided by 4 pi epsilon R square. What is the limit? 0 to 2 pi, that is 360 degree. This d theta vary from 0 to 360 degree rotation circle, because of ring it is 360 degree, right? So in this, lambda A cos alpha divided by 4 pi epsilon R square is constant, only we have d theta, right? So the integral d theta is theta. We have to substitute the limit 0 to 2 pi. So while substituting, what will happen? Lambda A cos alpha divided by 4 pi epsilon R square into 2 pi. Lower limit is 0, only 2 pi. This got cancelled. The 2 is there. So that lambda A cos alpha divided by 2 epsilon R square. Already we have the cos alpha value, that is h by r. Near the triangle it is available. So that lambda A h divided by 2 epsilon r cube. Finally we got the expression for electric field intensity due to the charged ring is E equal to lambda A h divided by 2 epsilon r cube. So in this video we got the expression for electric field intensity due to charged disk and charged ring.